Hello students, welcome back to my channel. Today we will study the topics of jam group theory, that is Sylow theory. We will learn about P groups, Sylow P groups, conjugate of a subset, some of the important theorems, that is Cauchy's theorem for finite abelian groups and finite groups. We will study the three Sylow theorems. We will study about frobenius theorem. We will also discuss some questions related to Sylow theory. Now, let's get started. Let's talk about P groups and Sylow P group. What is a P group basically? For P, P prime, a subgroup, H of group G is P subgroup if each element of H is power of if order of each element G be finite group if order of G is equal to P raised to power K, then for all A belonging to G, order of A divides P raised to power K, which in turn implies order of A is in power of P, which in turn implies G is a P group. Conversely, if G is a P group, then no prime other than P divide order of G, which in turn implies order of G is equal to some power of P. Hence, we arrive to the conclusion that G is a P group if and only if order of G is some power of P, that is P raised to power K. Now, let's talk about Sylow P subgroup of a finite group. Let G be finite group and P be prime such that P raised to power K divides order of G, but P raised to power K plus 1 does not divide the order of G, then any subgroup of order P raised to power K of G is called Sylow P subgroup of G. Hence, all the Sylow P subgroups of G are of same order, that is P raised to power K. And notation Sylow P G is set of all the Sylow P subgroups of G. Now, what is conjugate of a subset? Subset S. S the non-empty subset of group G and X be any element of G. Then conjugate of a subset of X determined by X is X inverse Sx equal to X inverse Sx for S belonging to capital F. Now let's discuss some of the important results related to Sylow theory. That is, number 1, Cauchy's theorem for abelian groups, which states that let G be finite abelian group and P divides order of G for P be prime, then there exists an element, non-identity element of G such that order of A is P. Also, if there exists K belonging to natural numbers such that K divides order of G, there exists a subgroup of G of order K. For abelian groups, it is also true for finite groups. Need not be an abelian, but this second condition is not true. Only first condition is true, that there exists a non-identity element of order P. Now, another result which we are going to discuss is Sylow's first, second, and third theorem, which states us that Sylow's first theorem, GB finite group of order n equal to p raised to power k n for k greater than or equal to 1, where p is prime and n belongs to a positive integer such that p and m ka GCD is 1, then we have that G has at least one subgroup of order p raised to power I for all I less than or equal to k. That is, every finite group has Sylow P subgroup. Sylow's second theorem states that G be finite group and P divides order of G, then all the Sylow P subgroups of G are conjugates of one another. Third, which we have is Sylow's third theorem states that G be finite group P divides order of G, then number of Sylow P subgroups of G are of the form 1 plus Tp for T belonging to positive integer, where 1 plus Tp divides the order of G. G be finite group and P divides order of G, then every P subgroup of G is contained in some Sylow P subgroup of G. Another result which we have is, if H is a Sylow P subgroup of G, then H is unique, basically only one Sylow P subgroup of G, if and only if H is a normal subgroup of G. And hence we have that G is not simple. Frobenius theorem states that for order of G equal to p raised to power m, or m greater than or equal to 1 such that GCD of p and m is 1, and if p raised to power r divides order of G, then G has a subgroup of order p raised to power r, and number of such subgroups is congruent to 1 modulo p, that is of the form 1 plus kp.